Okay, then we're all set up to continue with the second half. Sebastian's talk. Yes.
Yeah, thanks a lot. Actually, I should apologize. There was this question in the first half about group actions on the moduli space. And I think I forgot to say, well, I maybe said that if you morphism act, in fact, it's the mapping class. So you always have a mapping class group and that always ends. And always combine moduli. So, sorry about that.
No need to apologize for that. Are you apologizing for this?
Yeah. For giving an inaccurate answer. Okay, so let's recap associative submanifolds in a G2 manifold are calibrated by 3.5, which means they are minimal submanifolds. Actually, just a word, because that came out in the break as well. So being calibrated is, from an analytical point of view, a hopelessly overdetermined condition. And that is why the McMahon results about information theory don't use the calibrated condition, but the opposite. So for associative, you use psi to say what associative is. For coassociatives, you use phi. And for instantons, you also use psi. Okay, so we have these minimal submanifolds, and there is this spurious term of generic, which means that some strange differential operator is invertible. I believe you don't want to see any of those. And I couldn't tell you what these conditions mean in practice anyway. So the question that we had was, can one count associative submanifolds and get subtle invariants for G2 manifolds M phi in a similar way as, for example, in Gromov-Witten on Heller-Yau. Or there are these Flirt theories that you might have heard of. Something like that. And we also said that probably this associative counting, if it works at all, has to be done together with counting G2 instances. And you can read more about this in papers of Donaldson and Siegel or Heides Bartuski and other people who try to make sense of this. And now here's our first problem with naive counting. If you modify the 3.5, so if you move on the moduli space here, then it can happen that all of a sudden you have some associative submanifold coming out of nowhere and becoming two of them, or it can happen that we start out with one and then from one moment on you have two. The first one seems like you could count with signs and everything would be fine. But for the second one, that's a bit more tricky, obviously. Because you could count modulo 1. Okay. So here's an example of a bifurcation. Let's take a family of total 3G2 structures and assume we have two associatives like this. You must imagine 3 planes in a 7 space, but maybe lines in 3 space do the same job. And they come closer to each other. And at some point they will intersect, and then all of a sudden they will change the position and move away from each other. So far that's harmless. So we assume that at t equals 0 we have the self-intersection and otherwise everything is fine. But then at t equals 0 something strange happens. There will be a family of associative submanifolds plopping out of this picture, which looks like on the very right, so they come together, they look asymptotically conical, basically come together and then go away. And if you shrink this little cube in the middle, you get back to the self-intersection. Yeah. And this is expected to happen whenever this transversal self-intersection occurs. Each time you have a transversal self-intersection, one of these things plops out, or if you read the picture from the other direction, it goes away. That has been, I think, conjectured by Joyce, worked out by Nordström and Behra, And we even know what the local geometry of this thing is. It's supposed to look like a Lorna neck. That's something, some special Lagrangian in C3 that was found by Lorna in 1989. So, yeah, how does this relate? If you are on C3, you have a scalar form and you have a holomorphic volume form. And if you add one more trivial direction to the picture, you are on R7. Now, the 3 form comes by taking the scalar form times the extra variable. That's the 3 form, plus the holomorphic volume form, say the real part. And then you have to wonder what psi is, and psi will be then the imaginary part of the volume form, which this extra direction plus the square of it. Yeah. So we'll frequently work in C3 now to get a local picture and then say this embeds into a G2 situation. So now if you see this picture, I believe that some of you are immediately thinking about a scheme relation. Because that's what the picture for a scheme relation looks like. Except that, of course, I drew a 2-dimensional picture for something 7-dimensional, and here the abstract structure looks like a scheme relation, and that's why I'm presenting this talk to non-theorists in the hope that someone will kind of have a beautiful idea of how to deal with this, even if we are now in a higher dimensional situation. Okay. So, short summary, associative submanifolds are calibrated. We've heard that long enough. They're generically rigid, but otherwise very hard to control. They are expected to behave in a similar way as complex curves in Calabi-Yau manifolds. And then, I mean, I don't know, we haven't had talks about this, but I think there's a lot of higher category theory going on, starting from these complex curves in Calabi-Yau manifolds. So maybe this is also some point where you might find that some idea could apply in this context. Counting is tricky because of bifurcations, and there might be more problems that I'm not going to discuss. There are more problems, in fact, but nevertheless, there are conjectural counting schemes. One has been proposed by Joyce. This is for associatives where the 3-manifold itself has Betti number 0. If you have such a connected sum appearing, then what you would do is, I think, divide by the order of the fundamental group or something like that, and order of the, what is it? No, it's not the fundamental group. Dividing by the order of the first homology group somehow gives the weight which makes the count then work, even if you have connected sums. And Don Valkuski have a different proposal, but theirs only work if the first Betti number is larger than 1. So there is still a huge gap. And also the counting schemes, as far as I understand, are not really compatible. So I don't believe you find a common counting scheme which encompasses both of them. And now some pictures of associatives look like pictures from knot theory. You've seen that. And at least there is a relation between knot theory and complex curves. I heard talks by Eckmann and Schindler on this. So you consider holomorphic curves whose boundary lie on some special Lagrangians, then the boundary curves are actually real curves in a 3-dimensional Lagrangian, which looks locally like R3, and then you are in a situation where you can talk about knots again. Okay, any question up to here? Okay. So together with Andrew Heides, we started to think about these associative manifolds in a slightly different. We tried to get an overview of all possible associative submanifolds at once, basically, and we tried to get around the analytic problems for the start. So maybe we can postpone them for later and understand more of the topological structure of the things we're doing there. So I said counting by homology classes, well, we'll distinguish them by closely classes, which may or may not be a little finer than homology. but it's much coarser than considering homotopy classes, so manifolds inside this. Actually, if it's finer or not depends on the kind of topology theory that you use. You'll see this. Now, we are in a 7-manifold that is spin. And we have a 3-manifold that's oriented. Now you know that oriented 3-manifolds have trivial tangent bundle. And now you can conclude that then the normal bundle must be spin as well. And because the group spin 4 is disconnected, we can conclude that the normal bundle of an associative is always a trivial. However, there is not a natural trivialization, it's just the fact that you can trivialize it. So this means when we want to consider cobordism, we want to have some structure on the normal bundle of the associative. And we can basically pick any subgroup of SK cobord that we like. In fact, we could say spin, probably. But I'm not quite sure that there is no natural spin structure. There always is one, but it's not natural. So let's stick to S. Here are examples. If you take SO3, that means that you basically fix a non-vanishing normal vector field. That's something that Joyce does, and he calls this a flat associative. And we will see that we can say something from our point of view about choosing SO3 normal structures. We could also take one of the two copies of spin 3 inside SO4 and note that the way SO4 embeds into G2, these two embeddings of spin 3 are totally different. That's why I called one spin 3 and the other one SP1. One structure would describe the normal bundle as a spinor bundle for the associative, and the other one would describe the normal bundle as if we had fixed the trivialization of the tangent bundle of the associative. So this is quite complementary. There are other groups, and now whenever we have a submanifold and we have fixed a normal structure, normal G structure, we'll now call this a G submanifold. So this term will arise sometimes if I say G submanifold, it means submanifold with a normal G structure. Actually, the whole theory here could work in different settings. That you could try to do this for complex curves or bundles or whatever, probably with modifications, but the idea is not unique to the G2 world. Okay, so because I am in a probably analytically not too inclined audience, let's forget about the partial differential equations. And the way to do this, or one way to do this, is well, in the first place, you had a map F and you had its partial derivatives del I, and somehow there is some typo there. I guess the current length should be small as well. Sometimes it's easier to solve the PDE for functions f and fi and just forget that fi is supposed to be a derivative of f. Just write down the functions, find some functions that satisfy the PDE, and then afterwards you try to find a homotopy of this solution to an honest solution where the fi's are again derivatives of the f. And if it's possible to find such a homotopy to an honest solution, you say that an H principle holds for that particular partial differential equation. Actually, a good example is sphere inversion. So the immersing a submanifold into another manifold, that is a partial differential equation that satisfies, or relation, I should say, that satisfies an H principle, and that has been used to take a two-sphere in S3 and deform its real convergence to the same two-sphere but with inside. Yeah, and there are even videos from like 20 years ago, 25 years ago that show you how that's done. So that's a typical example of an H principle. And I said in the end of the last talk, we don't know if the H principle holds for tangent almost G2 structure. It means we don't know that we can deform a tangent almost G2 structure back to one of holonomy G2. Yeah. So now, instead of associative submanifolds, we'll consider three-dimensional submanifolds in our G2 manifold M. And instead of the tangent bundle, let's consider a three-dimensional subbundle of associative subspaces along A. We would get this for free if the manifold was associative, but if it's not, let's just pretend we find it. And that means we have now this almost associative. And this means we have forgotten the direction of the derivatives. Yeah. Equivalently, that's easier for us, we consider A as above, but instead of a three-dimensional vector bundle, we consider a four-dimensional one that's complementary to the three-dimensional. So this should be a bundle of coassociative subspaces. And this then allows us to pass to cohomotopy. So that's the basic fact. And I mean, I don't know, there are many topologists here, but I guess not everybody has seen the Confilag Tom construction. So let me give you a very short recap. Assume you have a Lie group and it has a fixed k-dimensional real representation, and we'll not mention this again, but it's always there. Then assume you have G submanifold n in some manifold M. So the normal bundle mu has a G structure. This G structure can be classified by a map from N to the classifying space BG, and this map is well defined up to homotopy. I guess most of you have seen that. Because of this, we can take the universal vector bundle associated with the representation over BG and can pull it back to N, and identify with the normal bundle mu. This is what this classification basically says. And in the next step, we take a tubular neighborhood of our submanifold and identify that properly with the pull back of VG. So now we have this map F bar from U to VG. It's proper. So if we go to infinity, if we go to the boundary of the tubular neighborhood, then we go to infinity in VG. And this means we can add one more point to VG. So MG is the one-point compactification of VG now. That's called the Tom space. And we complete our map by sending every point in M that is not in this neighborhood U to this additional point of infinity. Yeah, this is boring. But that's the Tom construction in one direction. The other direction is easier. If you have such a map, capital F, and you bring it into general position, then it will be transversal to BG. And this, you can view BG as a submanifold of codimension K in MG. Of course, BG and MG are all infinite dimensional and only well defined at the homotopy, but you can still make the statement. And it's still meaningful. So if you are transversal to that submanifold, then you take its free inverse, call it M, and you find out that you can get the map F bar over there by taking the derivative of capital F restricted to the normal bar. And you are exactly in the situation we had here. And so what Confilag and Tom really proved was, if you take coordinate classes of submanifolds with normal structure G in M, call this omega K GM, then this is isomorphic to the set of homotopy classes from M with an extra base point to the Tom space MG. Any questions? Yeah.
I don't see how your bundle that you fixed before relates to the G. So we discussed this bundle of three planes.
Yeah, I want to take a principal bundle to which this is associated. This should be a G principal bundles. And then actually I classify G principal bundles by these maps small f.
No, I meant on the slide before you had this bundle that was supposed to be like the tangent bundle of associative planes.
I'll take the normal bundle. I'll take the code associative planes. I'll come to that.
Okay.
So here, K is equal to 4 and G is a subgroup. So, okay. Other questions? So sorry for boring you with random constructions. So now we want to go to these homotopy associatives. So we need to find something like the Tom space for our problem. And it's best to have a bundle of Tom spaces. And that's what we are going to construct. So G is a subgroup of SO4. SO4 is a subgroup of BG2. So there is a map from the classifying space of BG to BG2. And if you take a good model, like you say, you take a huge contractible subspace on which all these groups act freely, and you take the quotients by G or by VG, then you automatically get a fiber bundle whose fiber is the homogeneous space G2 mod G. And we call this as G, as for associative. So that's the bundle of associative 3 planes in R7. And the extra G means with a fixed G structure on the complement. The complement is this four-dimensional. So this is this part of the picture here. And in the next step, we take the universal four-dimensional bundles over that. So we are the subgroup of SO4, so we take the standard representation of SO4 restricted to G and take the bundle associated with that. That also gives us a universal bundle over this associative plus minus on the left. Yeah. Then, in the next step, we do a one-point completion on the left. So we have YG, that's now the Tom space of this bundle, B as G over as G. And we use the G2 action on all this to form a bundle over BG2 with fiber YG, and this bundle is called XG. Okay. Now, we have one point at infinity for each point in BG2. Because each fiber over BG2 is a Tom space, each has a point at infinity, and we take iota for the moment to be this map, which sends the base point to the point at infinity. And if we collapse all these infinities to just one infinity, we get a space MG. And this is then actually the Tom space of the bundle BG to BG that we had on the previous slide. Okay. Yeah, sorry for this diagram with many colors, but there is much structure in here. And I want to try to get it all visible. So we'll regard this bundle XG as a bundle version of the Tom space from the last slide. Yeah, so we have also this projection from XG down to BG2. This is going to be important. So if you can't remember the whole diagram, try to remember only the maps P and Q. Yeah. And so now we have a bundle of Tom spaces over BG2. That was what we were trying to construct. Okay. So now I can say what the homotopy associative is. We start with a G Bordesman class alpha, represented by a map from M plus to MG. And we have a G2 structure, tau, classified by a map from M to BG2. And now what we want to have is a map F from M to XG, such that the lower triangle commutes on the nose. So we want to be exactly over the point in the classifying space of BG2 that we had fixed before. However, for the Bordesman classes, this is a bit too much to ask for, so we want that the upper triangle commutes only up to R. Which means that if we take Q after F, we get a description of some object in the same co-Bordesman class, but it would be a different thing. So let's write H asso G of M tau for the space of sections of the pullback of this bundle XG to M. And if we do that up to homotopy, let's call it HAGM tau. This means now that F is an element in the space of sections, and also that Q after M is on the vector. Now, this is our description of a homotopy G associative. And how do we get back to submanifolds? Well, XG contains a copy of BG. It's still a submanifold of codimension 4 in this infinite dimensional setting. So we can take its pre-image if we are in general position and call it A. And A then automatically represents the correct groups. Now consider the normal bundle to A. Then at each point of A, the differential of the map F will identify it with the universal bundle BG at that point. That's actually isomorphic to the associative, to the norm to this universal four-dimensional bundle of the associative Grassmann VSG at that time. And so this differential of F gives our normal bundle the structure that we want to have. Is this answering your question?
So, yeah, so are you saying that this rather complicated data upstairs concretely means you have a submanifold, the G structure in the normal bundle, and a bundle of associative three planes?
Yeah, except that I say coassociative forms, but
Yeah, okay.
yeah,
Okay.
yeah. Yeah, I find the other, this is more complicated than the other thing, but yeah, it's interesting. Okay. So if we have an associative submanifold, we repeat the Pontryagin-Thom construction. We want to turn this into a homotopy. So we start with the classifying map from M to BG2, and remember we have this BG bundle over BG2. And now, if we have an associative G submanifold, then it comes with the inclusion to M, and it also comes with the classifying map to BG for the normal bundle. So we have this little Bulbeck's graph. Okay. Now we identify the normal bundle with a tubular neighborhood in the whole G2 manifold M. And we would now like to get this commutative, but unfortunately that's not possible because U embeds into M. But it projects to A, so this the left-hand side distorted square cannot be commutative on the nose, but using fiber transport along little lines from A points in the tubular neighborhood, we can make it homotopy commutative. Same for the triangle upstairs. Yeah, so that's the best we get at this stage. And if we've done this nicely, then the map from U to BG is proper, and we can complete the picture by sending every other point in M to the particular point at infinity, sitting over the corresponding point in the classifying space of G2. Remember, we have more than one point at infinity, so we have to make sure that we end up in the right point at infinity. And this is basically how a homotopy associative remembers the G2 structure. This is because we have the different one at infinity and not just one. Yeah. Any questions on this part? Yeah.
Do we require that these two homotopies, these two twiddles are compatible in a certain sense, or?
Well, they have to be compatible in the sense that this almost square that you get from U via M to BG or from U via BG to BG2, this outer, let me see. So now it's the outer square. This one should commute in this. Okay, so we can go from homotopy associatives to maps into XG and back. And now let's look at the combined moduli space that we had before. So we have G2 structures and two associative G submanifolds. And should have written a little another G into that picture somehow. Yeah. And it has a forgetful map to the G2 moduli space. And we take the homotopy fiber of this map, and I claim that we can map the whole homotopy fiber of this map into our space of homotopy associatives. And if you if you forget all your category theory training and go back to good old textbooks of topology, then the homotopy fiber will be described as not as a holomb or whatever, a holomb, sorry, but as pairs of par in the base space. Here, the base space is the space of G2 structures. So we have such a path phi t of coordinate G2 structures starting at our fixed space structure phi 0 and going to some phi 1 and over phi 1. For phi 1, we have a true associative. Yeah, and then we can do the construction over phi 1 and use fiber transport to put it back to phi 0. So we see that we get the whole homotopy fiber of this combined moduli space inside our homotopy G associative space. And this means we can do all these constructions like this bifurcation construction that I showed before in one single space. So that's maybe one reason to set all this. Are there questions here? Well, yeah, H principle. So we might hope for a naive H principle, and this would say I take a homotopy associative and I then try to realize it as an element of this homotopy fiber, so which means I pick the G2 structure which is homotopic to the one that I'm in, and I can move my homotopy associative then to the true associative for that G2 structure. This would be very nice, but unfortunately it's wrong. I can prove this very quickly later that this doesn't hold. Okay, let's summarize. We have the Contrian-Tom construction, which identifies submanifolds with G structures, or rather the cobordism classes with homotopy classes maps. It's always helpful to go into homotopy somewhere, makes life easier sometimes. And now we want to mimic this, and therefore we replace the space mg by a space xg, which fibers into bg2, and then we basically repeat the construction. And homotopy associatives are now mapped to the space xg, but if you think geometrically, it's actually sections of a YG bundle tau star xg over M. So we have, for the non-homotopy theorists, we have also geometric explanation. And we have this modified Convergent construction, which relates this to true associative G submanifolds. And as I said, we capture the full homotopy between the combined modular space and the G2 modular space. So now, before I can show you something about singularities, I should do some computations. So first of all, can we represent a homology class in N, which is the same as a 4 cohomology class, by a G-bordism class? The answer is yes, that's always possible. That's also because the normal bundle is trivial and I can choose whatever structure I like. And is this representation unique? And indeed, by work of Tom, that's the case if we pick the full S4 as structure group, but there will be more choices to pick from if we go to some. Now, we've gone from homotopy classes to cobordism classes. Now, can we lift them up to homotopy associatives? The answer is yes, that always works. Is this unique? No. There are always more choices involved, and we'll try to compute some of them. And so we ask, what are the pre-images of homotopy classes of homotopy associatives over given cobordism? And do they have a geometric meaning? Well, let's see. At least a geometric description. So, any questions on this so far? No? So, as I said, Tom did some interesting computations. For example, he proved that this SO4 cobordism in the 7 manifold is the same as the force homology. And if we have a spin-7 manifold and we have other subgroups, then we get a surjective map from the algorithm theory into this one. This was because the normal one was trivial. And to understand the pre-images of the second map, obstruction theory, the naive way tells us that we compute relative homotopy groups. And in this case, for all L lower or equal to 8, this is a bit difficult if the group G is simply connected, like spin 3, sp1, or in the trivial group, then you have things to worry about. But if we take SO3, then it's much easier. So for SO3, the geometric description was we have a non-vanishing line field in the normal bundle, and for orientation reasons, I can assume I have a non-vanishing vector field. Okay? And adapting Joyce terminology, this is called a flag, and the manifold with a flag is called a flagged manifold. Corresponding Gottesman theory is then flag-oriented cobordism. And because the map from SO3 to SO4 is too connected, we see that these relative homotopy groups that we need for the obstruction theory vanish for all L up to 7 and become the integers in dimension 8. And so we can say that the integers act on this flag-oriented cobordism with quotient MSO4. In fact, the action is 3. And the idea of this is really similar to what I told you in the first talk when we were discussing the new invariant and G2 structure via the finners. So it's again taking connected sum with a 3 sphere and applying pi 3 and S3, which is the integers. That's how you get this action. So this was the cobordism side of the picture, and now let's go to the homotopy associatives. So here's my first theorem. If we have a G cobordism class M, call it alpha, and we have a G2 structure, just a topological G2 structure, forget about holonomy for the moment, then there always exists a homotopy G associative in that class alpha over tau. And there is a certain group which acts on all these equivalence classes of homotopy associatives such that the quotient of the cobordism space is the quotient of the homotopy associative set via this by this group, and the group itself is the co-kernel of a restriction map from the 8th homotopy group of Mg to the relative 8th homotopy group of Mg relative to Yg. Remember, Mg was the great Tom space for the group G. Yg was a Tom space for a restriction to one fiber of the bundle Bg over Bg2. So Yg really sits in Mg, and we can take this relative X mod. The group on the right is the integers. You can see that. And therefore, the co-kernel of R star is always a cyclic group. It means we have a cyclic group of choices going from G cobordism classes to G homotopy associatives. And now I can tell you there is no naive H principle. So we select class beta, say, in the second homology of M, and take it square. And remember from the first talk that phi evaluates on beta negatively. So if our cobordism class alpha represents the square, then phi evaluates on our submanifold alpha negatively. On the other hand, on an associative submanifold, phi is the volume form, so it always evaluates positively to the volume. So if we had a true associative A, we would get a contradiction. That means that this particular cobordism class cannot contain any G associatives for any G2 structure phi. So the whole homotopy fiber is excluded by this conjugate. Now you could say, what about two-connected seven manifolds? There is no beta. Well, bad luck. But then you take the first conjugate, which has exactly the same problem. Yeah. So you find classes which cannot be represented by associatives, and therefore we don't have an H. That's bad news. On the other hand, I wasn't trying to solve this problem. I was just trying to put it in a context which is more accessible from the point of view of homotopy. Questions so far? Yeah.
Focused on associatives, but you think you could set up something similar for coassociatives, and you think the H principle is also false in that setting?
Well, for coassociatives, they are not rigid, so I guess I would somehow have a different theory. I haven't actually thought about this, but it's something one could try. One could see if, for example, it's possible to get the whole family, the whole deformation family in this picture, at least principally. Yeah, but I haven't thought about this. So, more questions? Yeah. So, how do we prove this theorem? Well, we start from alpha, which is a map to energy, and then cell by cell, we lift it to put it back to xg. And if we trivialize our tangent bundle over the cell, that means we try to have to push a map to energy down the map into yg, because yg is the fiber of that. And this means we have to consider potential obstructions lying in this relative homotopy groups, energy relative to yg. And now you have a nice chain of isomorphisms. And it's best to read it from the bottom. You know that BG2 is reconnected. And you know from the way you prove the long exact sequence for fiber bundles that it's isomorphic to the relative group of BG relative to the fiber mass G. And then you have a Hurewicz isomorphism where L minus 4 is at most 4, so L is at most 8, up to the corresponding homology group. Then you have a Tom isomorphism. So you end up in the relative homology group of Mg relative to Yg. And because everything vanishes for L lower or equal than 7, you have another Hurewicz isomorphism, and then you are there. Yeah. Okay. Now, these are the obstructions against what? So I'm trying to find not only the map F, but also a homotopy between Q after F and alpha. However, ultimately, I'm not interested in the homotopy. I just want it to exist. So I have to divide out basically the choice of homotopies. Right. For L equal 8, the column is the integers, of course. But now I have to get rid of the homotopies, and that's by mapping in with the group PL of Mg. And the good thing is for L equal to 8, this is just now unstable G cobordism in the X sphere. So this is something that the ancient have computed in the case Tom. So we have results there. You can see what happens. There is a Hurewicz map, which is no longer an isomorphism for Mg. Then there is the Tom isomorphism, and then there is the small r lower star. And small r lower star is detected by the sum of the first Pontryagin class and the Euler class. This is a strange combination, and it's exactly the combination we need here. And you can evaluate this on generators of this unstable Bordism group in the X sphere to see what the kernel is going to be of the map from Mg, Yg to the space of actual homotopy cubes. So look for generators and see what they do. If the group is S4, then we know from Tom that the corresponding cobordism group is only the integers. And then it's not hard to detect that CP2 must be the generator because it has signature 1, there is nothing smaller. And the combination of normal Pontryagin class and normal Euler class is -3. so our co-kernel is C mod 3. If we take other groups, SO3 is interesting, of course. Well, we get another generator in the torsion subgroup, but the torsion subgroup maps to 0 necessarily, so it's still 0. For the other groups, like SP1, spin 3, and E, we only have torsion generators, so the integers survive. So this tells us how many choices we have to lift a cobordism class to a homotopy G associative. Let's summarize. We have bordism theory, an isomorphism from fourth cobordism to the fourth homology, and an integer many lifts to flagged cobordism. And if we pass the homotopy associatives, then it's 3 more choices on either side. Okay. And we've seen that each G cobordism class contains homotopy G associatives, and therefore there is no H. Now, final thing to talk about singularities. We have this space of sections of this bundle, which we call H associative G of M tau. And we've said that if F is transversal to BG, then we get submanifolds. And let the subspace where this happens, where F is transversal to BG, let's call this H regular. And this is a dense subspace, but it could be disconnected, and the various connected components would then be separated, hopefully, by sets where we can pass through mildly singular homotopy G associatives from one connected component to the next. There will be more severe singularities in higher codimensions, which we would have to study if we were interested in higher homotopy groups of this associative space. But let's stick to the codimension 1 case that's tricky enough. Actually, the same happens in the analytic description, but the codimensions of the singular sets might differ. And I'll give you an example for this in a moment. So we need to describe certain types of singularities to complete our overview, both of associative G submanifolds and of homotopy G associatives. Let's start with the easiest choice. Let's start with the strategy. That's good. We have a family of G2 structures, and we have a family of G associatives AT, which are submanifolds except at t equals 0. Then we try to construct an oriented cobordism between a minus t and a plus t for some t greater than 0. And there is no obstruction to that. We have seen that. That's possible. Because we are in one homology class, basically. Now we try to lift this to a G cobordism. And there might be obstacles. If necessary, however, we can modify the G structure because we've seen that there's enough way to do these modifications. So in the end, this lift will exist. And in the next step, we try to go up to xg. So we try to lift with respect to this collapse map from xg to mg and get capital F. And the obstruction against this lift F would then be the difference between A minus t and AT in the space of homotopy classes of homotopy associatives, not space set. And thus, we hope that we can see the passage through a singularity by a change either in the G cobordism class or in the homotopy G associative class. And we can try to compare this with results that people have obtained from the analysis of these problems. So here's a simple example. We have a family of G2 structures indexed by one parameter S, and we have a family of flagged associative submanifolds indexed by a parameter T, and we say that S equals T squared. So this was a picture you've seen on one of the first slides in the second half, this parabola here. representing two associatives coming together at one point in dimension. Now, this looks pretty generic here, but if you think in terms of topology, a whole three-manifold flows out of nothing. That's not really generic. What you would expect to happen is that you first have a zero handle coming out of nowhere, so you get a little three-sphere, and then you get more handles that you can attach to it until you have the full three submanifolds. That would be the topological picture to expect. However, from the analytic point of view, this cannot happen because if you have a zero handle popping out of nowhere, you have a very small three-sphere in the beginning. But a very small three-sphere has no chance to be a minimal three-sphere, let alone calibrated. So indeed, this is probably from the analytic point of view a generic situation, even though from topology it will stretch. So we still have to take care of it, even though we would believe we should do it differently. But let's see what happens. So the AT are what's called unobstructed. I called that generic in the first part of the talk, except that T equals 0. And if everything is set up nicely, then the Joyce orientation, which is actually the flag, will change. So we view each AT as a homotopy SO3 associative, and we consider the bordism that we get by taking the union of those. And if we take S as a bordism parameter going from negative S to positive S, then we see that 0 equals AT plus A minus T, as written down. However, Joyce tells us that AT and A minus T are not negative of each other, but they just point to a different orientation in the modular space. So if we want to kind of get in touch with this Joyce approach, first of all, we would not take the full flat SO3 cobordism, we would mod out by 2z, so we would distinguish only parities, not integers. And then we would have to identify minus A with A equipped with the opposite value. And then we would identify similarly this quotient of flat cobordism by this equivalence relation with the SO4 cobordism. And in that setup, we might even hope for a twisted H principle. Well, I mean, the obstacle we had a few slides ago was the wrong sign. But now this approach would allow us to remove the minus sign by changing the flag. I don't know if that's a good idea, but one could try this, or one would have to try this if one wants to connect to Joyce. And if we get an H principle, well, I doubt it, but at least the obstacle from the previous slides is no longer there. Okay, this was this example. Any questions? So let's go to the other one. Now a true isolated singularity at one point x0 and a0. And this is from the topological point of view, the generic situation. We pick one instance. But first of all, again, the strategy, if we have a cobordism between the manifold before and after the singularity, let's assume that actually there is a ball around x0 such that outside that ball, the manifold doesn't change at all. So all the strange things happen inside the ball, then I can restrict the cobordism to that ball and call it W, which is somehow a better letter for cobordisms, I find. And because outside nothing could change, we could try to see how the interior part of the bordism in that ball behaves if we restrict it to the boundary. And there, it would define for us, first of all, a coassociative frame on this four-dimensional bundle that we get from the interior, and then we could upgrade that to a G2 frame. So in the end, we would get a match from the boundary of W to G2. And we could use this map to determine the difference between the two homotopy associatives A minus and AT. And indeed, this means somehow I use the group to take a trivialized part of the normal bundle of the three manifold, then by connected sum, do something weird in the interior. So that's somehow the geometric way this works. Here's our good example of the transversal path intersection. And if we think about cobordisms, well, we could take this family, which was span a four plane, this would be a four plane, and they would intersect in one point. And if we could stabilize by moving up one dimension, we could make this true isotopy, but not in dimension 7. We would have to go up. So we have this transversal self-intersection, and as I said, the things are stably isotopic, but not isotopic. And remember, there was also this extra Lorentz that we have to incorporate. And this is what we do. We construct an SO4 cobordism W between the first and the second branch. There you see the blue and the green thing, and then in the middle, the brown stuff that's going to become the lower. And I guess this is hard to digest, so let's look at the lower half first. Now it's just the 3 disk times the real line, asymptotic, conically asymptotic to the end of the blue and the end of the green associative. And you see here in the picture that the green one is lying on top of the blue one. Yeah. You see also that the image has one critical point, and if you look correctly, it has index 1. That is because the boundary of the red piece is actually a 2-sphere, and we are inside 4 manifolds, so it's a 3 disk going up and it's 1 disk going down, which means we are performing a zero surgery to get from a minus to a 0. Now let's look at the other half. That looks pretty much the same, except that now you see that the blue associative is lying on top of the green one. And the critical point that we get here has index 3, so it's a 2 surgery, now from a 0 to a plus. Okay, here we go. And we can compute that we can first of all trivialize, can assume, say, that our frame that we are given normal to the associatives is trivial because, you know, they're just lying flatly inside this 8-dimensional space. So let's just assume that outside of this, everything is trivial, and then we can compute relative characteristic classes for the normal one of the cobordism, and we see the relative Pontryagin class is 0, the relative Euler class is 1, both for the lower half and for the upper half, so the sum of the two would be 2. And this now tells us, because P1 plus E describes the difference in the lifts, that we get all 3 different lifts of this associative to the space, to the set HASO4. Remember, there were 3 different lifts, and we see all of them. So all the branches that we have are different. Let's look at it from a different perspective. Regarding as an SO3 cobordism, we get different flags, but let's look at it like this. So here we have the 3 situations. Everything happens in C3, complex free space. I'm running out of time, so I'll be quick. There is a preferred flag which is perpendicular to C3, and we see if we take the cobordisms W minus W plus, we change this flag by 1. It's not respected by these cobordisms. However, true, at least from a minus to a plus, it is respected, which means this flag cobordism, the stable version, if you like, is preserved. Okay. So we've seen we realize all the lifts. We have seen we get different SO3 structures, and stably at least a plus and a minus look the same. But that's here because stably we can really move around without problems. So let me summarize we want to understand generic singularities to get an overview of the homotopy associative space. And we have seen two instances. There are some more, but time is out. Generic topological singularities are isolated and realized in surgery. We've seen one instance. There's also one where we perform a one surgery. And some geometrically generic singularities are not topologically generic. That was the first one. And the type of a homotopy G associative can change when we pass through a singularity. And how it changed depends on the structure group G that we've picked, and SO3 seems to be a good choice. Okay, going one step back. Remember, we have the space of homotopy G associatives, which captures the full homotopy fiber. We can use, we can study the regular homotopy G associatives together with the singularities that we like. And my upshot is that topology can help us maybe to understand the counting problems that I've alluded to at the beginning. Just as topology has helped to find the new invariant to distinguish the two structures. Then, in the end, we'll probably need some geometry to see what part of the topological concept actually is realized in the geometrical world and what not. But first of all, we would need some input. Like, for example, because we had a scheme relation, something like an associative not. Yeah, and maybe that's where I close. Sorry for going a little bit time.
Yeah, thanks, Sebastian, for this really nice talk. Questions for the speaker?
Yeah.
If the diffeomorphism group acts on the G2 structures, and let's say you have fixed G2 structures out, and the diffeomorphism then links if you calculate the action of the diffeomorphism group on this homotopy associatives.
No, not yet. You have the tools for doing this, might be interesting indeed. That's surgery theory in the end, isn't it?
Maybe
could be interesting to see what associatives can be realized that way, or related to each other that way.
One more question. So your homotopy associative seem to make sense for any topological space M. Is that right? I don't know if this is a benefit.
If you have a classifying map to be G2, you say, is it a benefit? Don't know. I mean, the point is, of course, I severely use cell complexes up to dimension 7 to do this homotopy calculations.
Yeah, this part is not applicable.
Yeah. Apart from that, it's maybe that.
Anyways, if there are no further questions, it's thanks, Sebastian, again.